Если хорошо, то давайте я начну. Во-первых, я хотел поблагодарить за приглашение сделать доклад на этом семинаре. Я надеюсь, что... Sorry. So first of all, I'd like to thank the organizers for inviting me to make a talk on this seminar. And I hope that the theory of normal forms I will explain today will be interesting for people from integrable systems and differential equations. So first of all, I'd like to explain what is a normal form of differential operators. Let me fix some notation. I will denote by dn the ring of differential operators, and I'll consider a very formal situation. If you like, you can imagine that the coefficient ring is a ring of smooth functions or analytic functions. K is the field of characteristic 0. But I prefer to work with ring of differential operators with coefficients in a formal power series ring in n variables. So K can be any field of characteristic 0. Again, if you like, you can imagine that K is just a field of complex numbers. And now I'd like to introduce another ring, which is very big and which seems to be very convenient because it contains practically all examples of quantum integrable systems. It contains not only differential operators, but also operators of integration, difference operators, mixed type operators, and so on. And I found several applications of this ring, and first application was found in our work with Igor Bourbon. It was published in 2020 about quantum Kalasher-Moser systems. And after that, I'll develop more technique concerning this ring, and the most recent results appeared in my paper in 2023, published in through D of Mian, and it is dedicated to the memory of Parsha. And the most fresh preprints about normal forms, which I'd like to explain today. So the ring, this universal ring, I denote as dn hat sim, and it can be thought of as some certain symmetric completion of the ring of differential operators. I tried to find an appropriate ring to study many examples of quantum integrable systems simultaneously, and I spent about 10 years, and finally, I think I found the most appropriate ring for study such systems. And let me explain the definition. So first, I define an infinite dimensional vector space. So let me denote Mn to be the vector space of formal power series where Ak are coefficients and the 3. And so I will use also notation R hat. It will denote just for shortness this ring of formal series. So this means that I consider multi-indices. K underline is equal to K1, Kn. With all, so this means that all Ki's greater or equal to 0. So this means that I consider only non-negative powers of differentiation. So this is a huge vector space. And now I define the special order function. So this is just a k-vector space. And then I define the order function ord. So in my paper, I use a notation bold ord, but here I cannot write down the bold ord. I just will write down this ord, which is underlined. And this order function on the elements of this vector space. The elements of this vector space I will call operators because, as I will show, they will act on this ring of functions. And let me introduce the order, define the order of any such element, of any such operator, to be the suprarum of sum of multi-indices minus v of ak, where v is a discrete valuation on this ring R hat defined by the maximal ideal. So this means that this V of AK is just a order vanishing of this function at 0. It's clear, I hope. And K, so K means just K1 plus Kn. And for example, V of x1 is equal to 1, V of 1 plus x1 is equal to 0, etc. So V of x1 power a1 x n power in is equal to sum of these indices. So this is just usual discrete valuation. So this suprarum is an integer number or infinity. Oh, infinity. And I put, as usual,
why the first equality? V of unit plus x1 is
because this element doesn't belong to the maximal ideal. It's invertible. And so this is 0. So if further I will explain everything for the ring of one variable, then it's just a discrete valuation defined by I1, where I1 is the power of x. Okay, but it can be extended to any number of variables. And as usual, I put the order of 0. So it's usual assumption in valuation theory that it's minus infinity. And then, now I give a definition of this ring Dn hat sim.
May I ask a question?
Yes.
Why not plus k? Why minus? It sort of looks like the plus is the most obvious choice. It's like the total degree or total height.
Yes, as I said. So as I said before, I spent a lot of years to find an appropriate completion.
That's kind of like the most important part.
Yes,
this minus works.
Yes, and this minus works. Moreover, so it's not this order is actually not something very new, because, for example, if you consider the Weil algebra and look at the paper by Dix-Mier, then this order will just consider with the one of orders of Dix-Mier, namely it coincides with the order 1 minus 1. It's a weighted order, weight y1, comma, minus 1. And this is just an extension. So it's very specific weight function. But as I said, it appears that this function works perfectly for applications which are interested to my tasks. So this is the answer. It's just
But
found
it's still a kind of like m-adic order function. So it has the behavior of some m-adic order with respect to which you can define completion.
We can, so you see, that since the link is not commutative, you can consider several variations of completions. Yeah. Say you can look in my earlier papers, I considered not symmetric completions, which also were pretty good for some reasons, for some tasks. But finally, when I tried to understand how to classify commutative subrings of differential operators, or more generally of difference operators, or differential difference operators, etc., I found that I need this version of completion which is the most perfect. And then I found this one. And as I said, the first time where this thing appears, it was our paper with Sigurd Burden, published in Proceedings of London Mathematical Society in 2008. It's about quantum collision motor systems. And then, okay, and then let me introduce the definition. The definition is very simple, actually. So I just define the n hat sim to be the set of operators such that the order of E is finite. And that is all. And 0, of course. 0 is minus infinity. It's okay. It's a very short definition. But it appears that this ring is very nice because it contains everything. It's a certain universal which contains practically everything you want. I mean, which you can meet in the theory of integrable systems or quantum integrable systems. So certainly, let me state that this is a ring. First of all, this associative, of course, non-commutative ring. So, and this ring contains the dense subring, the ring of differential operators, of course.
So when I say dense subring, you mean that this order thing induces a topology?
Yes, exactly.
What I was trying to get at.
Yes, yes, exactly. Okay. And also it contains practically all operators. Namely, so now let me introduce some notation because I will use it. For example, it contains all continuous endomorphisms of the ring R hat. They contains Dirac delta functions. Operators of integration with respect to the ith variable, shift operators, and so on. So that we can realize any operator in this ring. Also, it contains Lie algebras and so on. So,
for example, how Dirac's delta functions.
Just I will explain it just in 1 minute. Again, this observation is not something very new because it was known for people who deal with, say, deformation quantization. So this was known, but the ring itself is something new. So the typical example So let me consider the following operator P alpha, and I will use the following somehow standard notation of such type. What I mean here, so you can take and suppose that is U1, Un belongs to the maximal ideal of the ring. So they vanish at 0. Then what does this mean? It means that we can, we think that these variables commute. We can write down this exponent and then normalize it in such a way that differentiations go to the right-hand side and all functions on the left-hand side. Then, so this is some infinite sum of U alpha power something, D power something. So let me write down this exponential, this infinite sum. But then when you write down this formula, after that, when you normalize it, so by writing differentiation on the right and functions on the left, then you get an element from this ring. Because these functions belong to the ideal. So you can check that the series has finite order in this sense. So it's a well-defined element. And then it's just an exercise for a student, because anybody who studies calculus knows the Taylor power expansion formula. And we can apply it to any function. And notice that this is just an operator which realizes the shift functions of the following type. And so I forgot to say that you can also found that any element of this ring acts on the function. So this action is well defined. So actually in usual way. So if you will just apply this differential operators to this function and then multiply it with coefficient, then you will obtain a well-defined series, formal power series. And if you consider this power series as a Taylor expansion of some analytic function, say, then the formula will be correct.
By the way, and what is the order of Q alpha?
Looks like it's 0.
It depends on the order of this, on the order of these things.
Well, let's say U's are xi's. For xi's, it's 0, right?
No, for xi it's 0, right? But now let me consider quite explicit examples, because you asked me how to realize, and down the examples. So the delta I is just in these terms, it's just the exponential function of minus xi and delta I. Because if you look at this formula, it will kill exactly the i's component of this function. So and of course, this operator has order 0. That is correct. Then this example A. Then example B is that if you how you can realize the integral operator. You can take, yeah. We should take this one and multiply by di power minus 1. Then this series will belong to this ring, because when we kill unit here, the right-hand side will be divisible by di. So this is a series which belongs to the n hat c. And
minus first power allowed.
I want to explain this formula. So if you write down this expression,
Explicitly. Then it will. Yeah. Of
Yes,
course.
yes,
Ah,
yes.
so it's like a formal joining of a symbol that which makes sense
Yes,
after the fact.
yes,
after we get the
yes,
result.
yes, yes,
Mhm.
yes, yes. So it belongs still here, yeah, and it has order, of course, -1.
And what about the? So here's where Professor Zheglov believes, well, as I understood him, he
Yeah.
believes where things might get slippery. Is it true that once we join formally the symbol, the I inverse, is it true that it behaves as an element of some algebraic extension, of some algebra?
No, you see,
Is the algebra clear for this thing? Is it really a formal?
This is just,
again, it is
a
just
short.
it is just a short notation,
Shorthand,
short
yes,
notation.
shorthand,
It's
of course,
yes, it's not nothing more, because I don't join any formal element. It's just for notation. I define the series in this way. It belongs to the M hat sim. Yeah? It has order -1. And
then in your paper
Yeah.
recently, you mentioned
Yes.
Newton's polygons.
Yes,
And
yes, yes.
this sort of requires some algebraic rules for all this.
Yes,
So
but
this is why I'm asking this. Okay?
and after that you can
Interesting.
deduce these algebraic relations with integral and so on. Again, as I should say, that this formal integral operators like was known, for example, in works of Bavula, but Bavula considered just another question. He tried to prove, he is concentrated on the Dix-Meck conjecture. I was not concentrated on the Dix-Meck conjecture. I tried to prove another task. And Dix-Meck conjecture was just as a byproduct. I just noticed that these constructions can be applied to get something new. That was not my aim. And Bavula tried to consider the extension of L algebra with the help of these integral operators. And then he proved that the Dix-Meck conjecture for this extension is true. But in my paper, I found that just assigning the integral operator is not enough to get my results. We need to add also shift operators of special type, and then we will get a very interesting result, and I will explain it now. So I just want to explain some sort of notation and of examples. And the last example I will need is these shift operators, which plays a very important role in my situation. So just wait a moment. So notation is the following. So I fix k. Let me fix in this item some natural number k small, k big as a field, k small as a natural number, and fix a primitive root of unity. Psi k. So if we take arbitrary field of characteristic 0, of course, we need to extend it by joining this root of unity. But if we are working over complex numbers, then everything is okay. Then for any I n from z and q from 1 to n, I introduce the shift operators a, k, I, q to be equal to the exponent of psi ki minus 1 xi xq dq. So this is a shift operator, and it acts on a function in a very simple way. It just multiplies the i's variable, a q's variable, so on this power of the roots of unity. On the i's power of the root of unity. Okay, this is
The argument of number q, yes?
yes, as an argument of number q. So this is the main examples which I need for my talk today. Now I can go further. And now I would like to formulate two important theorems from my paper of 2023, dedicated to the memory of Parshin. Actually, these theorems play a crucial role here in all applications. My aim in that paper was to extend one part of the so-called higher dimensional Krichler correspondence. And in that paper, I established one-to-one correspondence between commutative subrings, which I call quasi-elliptic. They are subrings satisfying certain mild conditions, and certain subspaces of n-dimensional local field, so-called generalized Schur pairs. But I have no time to explain everything, but I just want to explain two theorems from that paper, which I really need to explain further results. The first theorem, it's a generalized version of famous Schur theorem. It says the following. So suppose we have n operators let there be commuting operators. And for simplicity, let's assume that they are all of order k, a fixed order k for any n. Now, finite order k, fixed order k.
K not equal to infinity.
No, of course, finite, because the order is finite in my ring, always, by definition. This,
yes, of course.
yes, this is just a notation. Let me introduce a couple of notations which I need to formulate the theorem. Another notation. I will introduce the notation f. It will be equal to the following left model. So this is a model. This left, right. The DN model. And as a space, as a vector space, it's just isomorphic to a space of all differential operators with constant coefficients. And of course, for any and another notation, that's the first notation. Another notation for any operator p in this ring, I define the highest symbol is in a very usual way. It's just a sum of all monomials of order equal to p. So it's alpha I xi di such that I minus how to such that I minus v of ai is equal to the order of p. So it's a usual definition extended to the situation. And now I continue the theorem. Assume I will call this module a spectral module. It is spectral, so the name comes with the theory of commuting differential operators. For example, if we consider this module as a module of some commutative ring of differential operators, then it can be shown under some mild conditions. And it is known in dimension 1 and in dimension n. It was proved in our paper by this Bourbon that the spectral module parameterizes the spaces of common eigenfunctions of commuting operators. So this is just the explanation of this name. But for a while, it's just a name. It's just some module. Now assume that the module M of F, sorry, of the ring. So if you consider the subring generated by all symbols, we can consider this F also as a module over the ring of such symbols. So assume that it's the module F of this ring is finitely generated and free. And this assumption usually satisfied for all quantum integrable systems. Then there exists an invertible operator in this ring Dn hat sim of order 0 such that s minus 1 di power k s is equal to pi or any I. So in other words, conjugating this pi with s, we get the powers of I. And this theorem is a clear generalization of a classical Schur theorem for the case of ring of pseudo-differential operators, which is very well known. But this statement, so it looks very similar. It's different because the ring is different, first of all, and the operator is different. So and the difference between my ring and Schur ring is huge, because the ring Dn hat sim is not Noetherian. It's not left Noetherian or right Noetherian. It contains many zero divisors. It has infinite dimension and so on and so far. Schur's ring of absolute differential operator is much nicer. It's Noetherian. It doesn't have any zero divisors, etc. So this operator, so statement is practically the same. The difference between Schur operator and my Schur operator is huge. So they're totally different. This is a first point.
2 questions.
Yeah.
First, what do you mean by module F for the ring?
So
You define module F for the ring?
yes, but this ring is contained here, and you can consider this.
You
yeah.
can.
Yeah.
The image of
Yes.
Sabrina. Okay.
Yes.
And the second, saying invertible, you mean that inverse operator also belongs to?
Yes, of course,
Okay.
of course. And it is for the zero.
Mm-hmm.
Yeah, this is all. So the first theorem, and the second theorem, the centralizer theorem. Now assume that we have some operator Q which commutes with all dki. The Q is in this ring. Now
With fixed K?
this fixed K, yes, as before. Then, so we want to describe the centralizer of all these powers. Then Q is a non-commutative polynomial C J1 Jn A K. What here? K is here the same. G1 1 A K Jn N, where all coefficients C G1 Jn are polynomials in variables dq integral q with constant coefficients and the degree. So the degree of this polynomial C G1 Gn with respect to integral is less or equal to k minus 1, and the degree of these polynomials with respect to the differentiation is less or equal to the order of q. So this is the statement. So the centralizer consists of non-commutative polynomials of restricted orders in 3 types of variables: differentiations, integrations, and shift operators. And the most important thing that they are of restricted order. So we see this is a statement. And now let me give some example how it works. Now I came closer to the definition of a normal form. And let me illustrate it in the case of one variable, just one variable. So let me begin with a remark. If the number of variables is equal to 1, then the assumption of Schur theorem is satisfied for all, so for any regular operator. Operator P. What means regular? Regular, by definition, means that d power k multiplied by p, it's modulo this maximal ideal and d1 hat c is not equal to 0 for any q greater or equal to 0. For example, any monic differential operator P just on the ring of differential operators is regular, because these operators look like this one, sum 0, and if you will multiply this operator on the left with any power of t and then take it modulo this ideal, so just taking it all functions at 0, then it will never be 0. So it's clear. So this means that for any differential operator, monic differential operator, this is a regular operator. Moreover, if a coefficient is an invertible function, then it's also regular by the same reason. So that means that for the case of dimension 1, this Schur theorem works practically for all reasonable operators. And then okay. Then let me introduce the definition of a normal form. And then I will explain what is this on the example. Let B be a commutative subring containing n operators P1, Pn as in Schur theorem. Generalized Schur theorem. Then we'll call the ring B prime S B S minus 1 a normal form this is a normal form of B with respect to the fixed operators P1, Pn. So this B prime, it belongs.
S that normalizes P.
Yes. This S from Schur theorem. And by definition, this B prime belongs to the centralizer of this set of operators, the centralizer. And so that means that any element of this ring is a non-commutative polynomial in operators of differentiation, integration, and shift operators with constant coefficient. And of course, this normal form is not uniquely defined, because the Schur operator is not uniquely defined, but it's defined up to multiplication with the operator from the centralizer. This centralizer is described by the centralizer theorem. However, we can normalize this normal form in some sense, in some put in some additional conditions, and then we'll find some interesting applications of this construction. So the P prime is not uniquely defined, but up to conjugation with S is equal to 0 and S belongs to the same centralizer. But nevertheless, we can normalize it in some sense. So now let me explain one example. But what is interesting is that the normal form. So if we consider some finitely generated subring B, then since the normal form consists of non-commutative polynomials of restricted order, we can always calculate the normal forms of generators explicitly for any given example of commuting operators, of a ring of commuting operators. And it's a remarkable fact. For example, let's take n is equal to 1, and let's consider the example of very well-known Wallenberg operators. These are ordinary differential operators of order 2 and 3. So, and U is some potential which we assume to be a series It's known that these operators commute if and only if U satisfies the KdV equation. Okay, then what we can do? The first thing which everybody can try to do is just to compute the normal form of, say, operator P with respect to L. We can find the Schur operator up to certain terms, and then calculate the normal form explicitly. The normal form even normalized normal form in certain sense of P with respect to L can be described as the following formula. So P prime is equal to, it's explicitly was found by my students and checked independently. So this is just a computer calculation, but it's not difficult in this case. And everybody can check that it is correct. A2, 1. So since the variable is 1 here, I omit the second index. E2 means that it is we need to take usual square root of unity, and 1 means that it's a multiplication of the variable by -1. And plus plus 4d power 3 minus 2 u0 square plus v2 to integral. So this is a normal form of p with respect to L. It depends on 3 parameters from the scalar power extension. So u0, u1, and u2. And so this is just an example, but since it's a non-commutative polynomial for circuit order, I can compute it for any given commuting, say, ordinary differential operators. Independently of this potential, it can be a p function, degenerations of p functions, everything you want. So it is just a question of calculations. It's just always non-commutative polynomial. Okay. And now let me continue this example. So another remarkable fact, which can be proved in the case n is equal to 1, then in fact this centralizer is isomorphic to a matrix ring over k d power k over polynomial rings of such form. And this fact can be used to find very interesting applications of normal forms. The first application, which was found in our recent preprint with my PhD student Chunhu Guo from Beijing, is explicit parameterization of modulus space of so-called spectral sheaves. Let me recall just very briefly. Of spectral sheaves. So let me recall that by the very well-known Krishyer theorem, so the Krishyer classification, so any ring of commutative ordinary differential operators can be encoded. So you can take some equivalent classes where B1 is equivalent to B2 if and only if they are conjugated by some invertible function. In terms of spectral data, let me write down them in the following way. Where C is a projective curve. In Krishker's works, C was smooth curve because he considered only rings on general position. But further later, this theorem was improved and generalized by Mumford, Drinfeld. So there are many authors. Mulasse was the last who works on this. And this correspondence was established for any projective curve over any field K of characteristic 0. P is a regular k point. So if k is a complex numbers, then everything is clear. So that is a local parameter at P. And F is a torsion-free sheaf, or if C is smooth, and it's just a vector bundle, as in Krichever's work. With vanishing cohomologies. And phi, there are two versions of these results. Yeah, let me, phi I will write down on another side of the blackboard, because it's not so important for us. The phi, so there are two versions of this classification theorem. In Krichever's classification theorem, phi consisted of r minus 1 transcendental functions and so on. But in Mumford's classification, it was just a trivialization at the point P. And since it is shorter, let me just use this notation by Krichever. So I can write down the Krichever theorem, but it will take more time. So to say, I want to save time and not write down this version, because it just will take more time.
It is inessential.
Yes.
We can skip.
Yes, because it's just, in fact, this part of spectral data is very important because from the point of view of integrable systems, the people are interested in explicit solutions of equations like KdV, Kp, or Kp hierarchy, and so on. The most important achievement of Krichever was the explicit formula for the Baker-Kaiser function, or for common eigenfunctions of all commuting operators, in case when the rank is equal to 1. When rank is equal to 1, we can just forget about this trivialization. It is not essential at all. And then, in this case, we can write down explicitly, in terms of theta functions, a common eigenfunction of all commuting operators in this ring. This was the most important achievement by Krichever. But if the ring has rank more than 1, the rank of B is just the greatest common divisor of all orders of P on B. So here, rank R rings corresponds to rank R sheaves. And the most pleasant correspondence is in case of rank 1. Then we can forget about this part of spectral data, consider only geometry. And then we can write down explicit formula of common eigenfunctions of operators in this ring in terms of theta functions of this curve. See, it's a Krichever formula. This is a point. In the case when the curve is smooth. If it is not smooth, then the explicit formula again exists, but it will be more complicated. It will be some degeneration of Krichever formula if we deform the curve. But let me fix this notation. And now, the first application of normal forms is an explicit parametrization of the moduli space of such sheaves. I call such sheaves as spectral sheaves. So the spectral sheaf is a torsion-free sheaf with vanishing cohomologies. We can consider rank 1 sheaves or rank R sheaves. It's not important, and also any arbitrary curve. And the natural question appears how we can parameterize them explicitly. And the question I was interested in is an extension of this parameterization to higher dimensions. I tried to extend this one-to-one correspondence to the case of rings, commutative subrings of n variables, more than one. And in this case, this one-to-one correspondence can be extended, and the spectral data will consist of algebraic varieties and shifts of higher dimension. And then in higher dimensions, the following question appear: when the moduli space of torsion-free shifts with certain conditional cohomology is non-empty. If it can find such an algebraic variety, such that the moduli space is non-empty, then we can construct some example of quantum mutable systems and vice versa. In dimension 1, any curve has a non-empty and very rich moduli space of such shifts. But in higher dimension, it's not true. And the question is how to find them, how to classify them. And the normal form will give a potential answer on this question. And the first step was to introduce an explicit parameterization of these shifts in terms of normal forms. And the answer, the example is still written here. And the first result is an application of normal forms to parameterization of spectral shifts. What we need to do, for example, to parameterize all such shifts in terms of local coordinates, to say, we need to make the following thing. We take so the spectral curve in this example of P and L in this example looks like this one. We can compute it again quite explicitly. And minus 4 0 cube plus u1 square minus 2 u0 u2. Very well. Now assume we want to fix a curve. This will be some elliptic curve given by this equation. Then we get two equations. And this coefficient will be equal to assume we fix G2 and G3. So we fix the equation of a spectral curve. Then the answer is the following. Spectral shifts are parameterized by points in affine three-dimensional space U1, U0, U1, U2, satisfying these two equations. So any point of this affine algebraic set corresponds to the isomorphism class of such shift, and vice versa. So the receipt is very simple. Assume we have very complicated curve. You want to parameterize and to find a modular space of shifts with vanishing cohomologies. What we need to do? We need to fix the some normal form. For example, if you know that this is a spectral curve of operators of order n and m, we fix d power n, and then the normal form of p with respect to L will always be some matrix or some operator of restricted order with constant coefficients, like this one, for example, with some unknown coefficients. But since it's a polynomial of restricted order, there are only finitely many coefficients. This is a dimension of a fine space where we can embed our moduli space. Then we substitute this normal form to the equation of spectral curve. And then we get a set of equations on these coefficients of normal forms. And then the statement is that the points of this algebraic set are in one-to-one correspondence with sheaves of vanishing cohomologies. So this is the first statement. And then second application, since I think my time.
You're not very restricted.
Okay. And then just the idea how to it works. The details are written in our first preprint. And then what can be interesting to you. Now I want to explain the second application of this normal form, namely how we can really relate the solutions of string equation to the pairs of commuting differential operators of order 1. And this is an application to the Dixmere conjecture. So the first application is a parameterization of spectral sheaves. And second application is this one. Okay. So application 2, the string equation. So by string equation, I will understand the following relation, where P and L are differential operators, just differential operators. The question is how to find a solution to string equation. There was some series of works by Grinevich and Novikov in 90s. I hope these works are known to you. Where they found several examples of solutions to the string equation. And they studied the solutions of them. But there are just examples. Maxim Pavlov told me that, and I think it's also very well known since that time, that the solutions to the string equation correspond to the solution of the Pelny-Weber equation, as far as I remember. And the question was how to relate. So he thought that the solutions to the string equation are related to the commuting differential operators. So that was his prediction. Now I want to explain that this prediction is true, and really we can relate solutions to the string equation to commuting differential operators. And even more precisely, we can describe the way how to construct solutions of the string equation from the pairs of commuting ordinary differential equations. Namely, we have the following claim. Assume that P and L are solutions to the string equation which belong to the first Welle algebra. The first Welle algebra is just a ring of differential operators with polynomial coefficients. So clearly it belongs to the one. And PL is equal to 1. Then this pair, determines some endomorphism. And let me recall that in this case, so this partial case, so if you find a solution of string equation inside a Welle algebra, then analysis and algebra meets. This pair determines an endomorphism of the first Welle algebra, and the Dixmere conjecture asks asks that the non-zero endomorphisms of the first Welle algebra is equal to the automorphisms of the first Welle algebra.
Why no zero though? The zero map is not an algebra endomorphism because it sends 1 to 0.
No,
And
it's
so
it's
you get
endomorphism. It's
algebra.
endomorphism, but it can be an automorphism. It's zero endomorphism.
Sorry. Okay, then what do you mean by zero then?
Zero endomorphism. So everything goes to zero.
But it's not an algebra map. It's not an algebra homomorphism because an algebra homomorphism must map one to one.
Well, if you
the unit into itself.
if you say that we consider K algebra endomorphism,
Yeah.
then yes. But
and so this endomorphisms of the wide algebra is not algebra endomorphism.
okay. Let's if you put here K, then we can forget about that.
Okay.
It's just a question
Just
of definition. Yes.
Yeah.
yes.
Okay.
But any endomorphism is exactly given by a pair, which is a solution to the string equation, vice versa. Then Diximier itself described a group of automorphisms of the first Welle algebra in his paper by. He proved that the automorphism group of the first Welle algebra is generated by tame automorphisms. And tame automorphisms just send t plus some polynomial of x and x to x, and vice versa, x to x plus polynomial of d and d to d. So if you will compose these are some polynomials and x and t correspond to them. If we compose this tame automorphisms, then we will get the whole group of automorphisms of the first Welle algebra. Now, the natural question when I began to study these normal forms was very obvious. The obvious question was, what is the normal form for solution to the string equation, independently if this belongs to the ring of differential operators or to the ring of Welle algebra. This is an obvious question. So let's say the order of P be equal to n, the order of Q, L will be equal to m. And then the question, what is a normal form? Of L with respect to
the order without the underline. The order is just the
usual
the
order.
degree with respect to d.
Yes, it's a usual order.
I'm a bit out of the loop on this one because
Yes.
Because
Yes. And let me write down one remark. So the order. So if P is a differential operators and P is monic, or if the first coefficient, the highest coefficients of P is an invertible function, then the usual order of P will coincide with my order of P. This is very well. So, and now we need some reductions. So what is known, I just will say 2 words about what is known about the automorphisms and endomorphisms of, say, solutions to the Welle algebra. It is known The usual fact is without lot of the most obvious fact is that without loss of generality, we can assume that the order of P is equal to the order of P, so that the highest coefficient is noise invertible, and that correspondingly order of Q is equal to the L is equal to the order of L. Then what is known? By using the technique of Newton polygons for elements of the Weyl algebra, people understood that endomorphisms and automorphisms are different in the following way. So if P and L determine an automorphism, then the Newton polygons are of triangular type. So, and moreover, so if it's say D, here is X, so that means that they are inside this triangle, and the same is for Q, for A, sorry. And moreover, the order of P divides the order of L, or vice versa. And if PL determine an endomorphism, which is not an automorphism, so the conjecture assumes that it's not impossible, that it's not possible, but however, if it exists, then and if P and L determines an endomorphism, which is not an automorphism, then without loss of generality, so without loss of generality means that we can compose it, this endomorphism with some automorphism. P and L are of so-called subrectangular type. It is written in the paper by three Latin American mathematicians, Guccione, and Valcui.
What does it mean?
I will explain. This means that the Newton polygons are rectangulars. So that means that all monomials lie in some rectangle, and this vertex, the main vertex of this rectangle, belongs to the Newton polygon. So everything is inside, and the vertex must belong to the for both. And moreover, it's also for L. And moreover, the order of P is not divisible by the order and vice versa. So no order of P divides order of L, not order of L divides order of P. So the question is whether exists such pairs which gives a solution to the string equation which are of subrectangular type and with this condition. And also it is known that these rectangulars cannot be squares. So they are always not squares. It is what was known up to now. And then I consider the following natural question. What is the normal form of the solution to the string equation? Then the proposition of the normal form of P of L with respect to P is as follows. So so P prime is just D power n, right? And Q prime, so we apply the Schur operator to P prime, we obtain D power n, and Q prime it is some element of the centralizer, which is a matrix ring. In fact, so it can be written either as a matrix or as a non-commutative polynomial of finite order. But it looks as follows. It looks like Q prime tilde. Q prime tilde. This belongs to the centralizer. Plus Q prime minus n, and I will call it as a tail. It's a homogeneous operator of order minus n. So this part commutes with d power n, but this part not commutes with this power n, and it's exactly gives us an operator whose commutator with d power n is equal to 1. And d power n is q prime minus n is equal to 1. But in fact, this q prime minus n can be explicitly found. And
well, excuse me.
Yeah.
By normal form for the string problem, you mean you reduce the first operator to the normal form, because your definition was concerned with commuting.
Yes, but you are right. But actually, these theorems, Schur theorem and Gauss theorem, works in arbitrary case. So my natural and I can also introduce the notion of a normal form for any also non-commuting operators. Then I just take operator, consider the corresponding Schur operator, and then apply it. And I then I get a notion of a normal form of a non-commuting operator, and it has very specific type. So it has a type of an element of centralizer plus some tail, and this tail can be explicitly given. So I don't want to spend much time here. It can be explicitly given. I just let me write down this one, because then I need to show the explicit formulas. It's not very difficult. It's just a question of calculation, because it's a polynomial in shift operators, and so it looks like some constant by xd plus sum of ai's, ani's with some coefficients. So all coefficients can be explicitly given, found. So it's not difficult. It's just a question of calculation. And then the following natural question appear. What is the relation of this centralizer part and this part. The statement is that if you have a solution to the string equation, then this pair d power n and q tilde prime is a normal form of some commuting differential operators of coprime orders. That means that the rank of the ring of corresponding differential operators is 1, and it is the most pleasant thing. That means that coefficients of corresponding differential operators can be explicitly given in terms of theta functions of spectral curve. So the theorem is that so if P and L is equal to 1, then the pair d power n and this q prime tilde is a normal form of a pair P prime L prime of commuting differential operators. And the rank of K of P prime Q prime
Because Q prime is in the centralizer, yeah?
The point is, no, the point is that if you take any element from the centralizer, this pair is not always the normal form of some commuting differential operators. And it's a very delicate point here, because in fact, we can, as I said before, this ring D n hat sim contains everything. For example, with another my student, we studied commuting difference operators by Mironov, Moulesheva, by Khrushchev and Mumford. They can also be embedded to this ring D n hat sim. And we also calculated the normal forms of these operators. The normal forms of difference operators also will consist of such a pair, d power n and something from the centralizer. But they are not always considered as a normal form of differential operators. And so not any pair gives us a pair of differential operators. So some pairs can lead us to difference operators, some pair can lead us to integral operators, and so on. Yes, it's a very amazing thing. And the theorem is deep enough, so I could be able to prove using the technique from this theory of commuting differential operators. So what I observed that I can construct by such a pair, a sure pair in the sense of Presley, Siegel, and Lasse, which, due to the extended classification theorem by Mumford, etc., give us a pair of commuting differential operators. This is a point. So that's a very delicate point of view. So not any pair leads to differential operators, but for solutions of string equation, it will lead to a pair of commuting differential operators. And moreover, it will to a pair of commuting differential operators of rank 1 with very specific spectral curve. And the claim is with a spectral curve, some spectral curve of the form. So it has some specific form. It looks like, so let me introduce a notation. So if D is the greatest common divisor of n and m, then it looks like this one. So it will be x power m divided by d plus some coefficient alpha y n divided by d power d plus some tail. This tail consists of monomials of Dixmuir weight mn less than m dot n. So here the weight is m dot n. All other monomials less of this weight. Again, we can write down a picture, the Newton polygon of this F. It looks like this one. So this is a line. This line corresponds to this term, this highest term, and all other monomials belongs somewhere here. But another specific term, specific condition here is that is that the solution. So if it considers the Puiseux series of this polynomial, so that power dn plus y is that power dm. Then at some point, so this solution of this if p is the first exponent of the power of d, which is not which is coprime with d, then this dn minus p is always greater or equal to n plus m minus 1. So this distance is of this, has this property. This is a theorem about the corresponding commuting differential operators, and vice versa. And vice versa. Any commuting pair of differential operators p prime and l prime with such a spectral curve leads to a solution of the string equation. So this is a characterization of all solutions to the string equation in the ring of differential operators. In the ring of differential operators. So if I take any spectral curve given by this polynomial with this property on the Puiseux solution, then according to the classification theorem by Krichever and others, I always can find a huge number of such commuting pairs of operators. Actually, these pairs are parameterized by a moduli space of spectral sheaves, and this moduli space of spectral sheaves are parameterized also with the help of normal forms. And for any such pair, I can construct a solution to the string equation. Now, for the Wheel algebra, I can explicitly say that this estimation becomes an equality if and only if this pair gives an endomorphism without automorphism. And in all other cases, so for automorphisms, we have strict inequality here. And this is a characterization of endomorphisms which are not automorphisms. This is a result which I wanted to point out here. And then, I hope, this can be used to attack the Dix-Mier problem. But however, for people from integrable systems, at least for, I think, for Maxim Pavlov, it will be interesting to consider also the solutions to the string equation in differential operators. And this is a second application of normal forms in dimension 1. In higher dimensions, I also expect the corresponding parameterization of moduli spaces. And this was my original aim, to understand how to do it in higher dimensions. But occasionally I found that we can say something also in dimension 1. And this is all for today, I think. If you want to know more details, then...
Thanks a lot. Yeah. Please.
Yeah.
Microphone.
Yeah. Okay.
Okay, thanks a lot. Questions, remarks? No question, no remark. Okay, then, thanks a lot again.
Okay.
And, well, hopefully this is the part 1.
Yes.
Okay. Well, thanks for being with us, and goodbye. We meet next Wednesday, but the time is unusual. We'll meet at 4 a.m. Moscow time, because our speaker will be from Japan.